Welcome everyone. Today we're going to continue talking about partial fractions and specifically how we can use that technique to help us integrate functions. So we're going to look at a few kind of special cases and applications in today's lesson, and we're going to start by first considering irreducible quadratics. So we know that when we go through a partial fraction decomposition, we sometimes end up with an irreducible quadratic term. It just happens. And so far we've seen how to integrate those terms of the form x squared plus a squared, those irreducible quadratics. And we have these two nice integral formulas here. The integral of x over x squared plus a squared is equal to 1/2 natural log of absolute value x squared plus a squared. That's a u substitution. And then we also have this one, the integral of 1 over x squared plus a squared, and that involves inverse tan. So 1 over a times inverse tan of x over a. So those are our two kind of integral formulas that we rely on here. And they only have the format of x squared plus a squared in the denominator. But we know, we've seen them, there's other types of irreducible quadratics out there, more generally of the form ax squared plus bx plus c. So how are we going to be able to integrate fractions where we have that irreducible quadratic in the denominator? Well, completing the square. So we're going to be able to use completing the square. So if we have ax squared plus bx plus c, if that's our irreducible quadratic, we're going to be able to use completing the square plus a u substitution. Told you u substitution. That's our go-to strategy here. So it always kind of works its way into these problems. So we're going to do both. We're going to do a completing the square and a u substitution. And that's essentially going to convert it from this format into our other format. So we'll get something of the form u squared plus a squared form. So let's see how we're going to do this. And we'll look at an example to guide us here. So let's do the integral of x plus 3 over x squared plus 4x plus 13. Now this is a rational function, so we would try to do the partial fraction decomposition. So we would look to see if this factors any further, but it doesn't. This is an irreducible quadratic. And you could check that with the quadratic formula if you want. Doesn't factor any further. All right, so how are we going to do this? Well, we're going to, and it's also not part of it's not one of those forms. It's not x squared plus a squared. We have something else in here, this 4x, that is really we have to adjust for that. And so we're going to use completing the square on this denominator. So let's see how this is going to look. So let's write down our quadratic here, x squared plus 4x. And for completing the square, we want to leave a little bit of a space here because we're gonna be putting some things in. So let's put the plus 13 off to the side here. All right, so how does completing the square work? Well, it usually works nice if the coefficient in front of the x squared is a 1, and that's what we have here. So when that's the case, we can take this number that's in front of our x, and we can divide that by 2. So 4x, or the 4 divided by 2 gives us 2. Then we take this number and we square it. So when we square 2, that gives us 4. So we're going to add in 4. Now we can't just add in something because that's going to change our function, so we have to subtract it out right away. And how completing the square works is we group these terms together, and then we group these terms together. So the x squared plus 4x plus 4, that's going to factor very nicely, and that's going to factor into x plus 2 squared. Now, how do I know x plus 2? Well, because I have this 2 down here, and that's telling me that I'm going to be having this x plus 2 right in here. And then what other terms am I going to have outside of this factoring? Well, I have this minus 4 plus 13. That's going to be plus 9. So we can rewrite our integral then with this completing the square thrown in. So our integral is going to become x plus 3 over x plus 2 squared plus 9. Now the completing the square, that helped. It's still not in the exact format that we need to use those integral formulas. So at this point, we see this x plus 2 inside the parentheses. We're going to do a u substitution where we let u equal the x plus 2. And we know with the u substitution, we're going to calculate du. So derivative of x plus 2 is just 1, so we have du is equal to dx. And we're going to put all of our pieces in. Now, we have this x plus 3 up here. So there's various ways we could handle that. We could solve this equation for x. Or if we added 1 to both sides, that would give us an x plus 3. So we get u plus 1 is equal to x plus 3. So we could either solve this for x or get a little clever and just add 1 to both sides, and that tells us what x plus 3 is. You get the same result either way. All right, so now we have all of our ingredients. Let's put everything in. So we're going to have the integral. Now the x plus 3 in the numerator here is going to become u plus 1. The x plus 2 is going to become u, so we end up with u squared plus 9 in the denominator. And then our differential dx, we know, is going to become our du. So there we go. We end up with the integral of u plus 1 over u squared plus 9. And now this is of the right format for us to use our two integral formulas. So let's kind of go through that process. We're going to break this up. So we'll break it up into u over u squared plus 9 plus 1 over u squared plus 9 du. So that's kind of our general strategy for when we have these irreducible quadratic fractions. We generally split this up into two separate fractions, because how we integrate the first fraction is going to be different from how we integrate the second fraction. So that first fraction, we know what that is. So these are our two kind of important integrals here. So let's just go back. When it's x over x squared plus a squared, it's 1/2 the natural log of the denominator. And then when it's 1 over x squared plus a squared, that's our inverse tangent one. So let's apply those two formulas. So integrating this u over u squared plus 9, we're going to end up with 1/2 natural log absolute value u squared plus 9. Now technically here the absolute value isn't necessary because u squared and 9 are both positive. So this whole thing inside the log function here is positive. So really we don't have to worry about the absolute value. But it's just kind of a good habit to be in anyways. Then we want to integrate this 1 over u squared plus 9, and that's going to involve our inverse trig function, or inverse tan function. And the only thing we need to figure out is the a value that goes with it. So we look at that positive constant that we have there, and that tells us a is equal to the square root of 9. So a is equal to 3 in that integral formula. So we're going to end up with a 1/3 in front, and then it'll be u over 3, as our inside our inverse tan function. So that's just that trig, that integral formula on the previous page. Then we have our plus c. There we go. So this is looking better. We have our antiderivative now, but we still have to convert back to x. So we did do a u substitution here, so we have to convert back to the original variable. So let's convert back. So what was u? Well, it was x plus 2. So we end up with x plus 2 squared plus 9. And then we have our plus 1/3 inverse tangent. And then what was u here? So basically we're going through, and wherever we see a u, we're replacing that with what we set u equal to, x plus 2 in this case. So we're going to have x plus 2 over 3. And then, of course, our c there at the end. And there we go. We have our antiderivative all in terms of x. If you want to have a little bit of fun, x plus 2 squared, we can multiply that out, add in the 9, and we already know what this is equal to. Going back to our completing the square, it was just equal to our original irreducible quadratic. So we could rewrite this as the absolute value of x squared plus 4x plus 13 all inside our log function, and then everything else is just going to, stay the same. And there we go. We have our antiderivative. So this example really illustrates what happens when we have a more general irreducible quadratic. All right. So this was just a kind of a special case that we had to consider. Now, we're actually going to shift gears just a little bit, but we still are going to use partial fractions. And the next little topic here is kind of doing a rationalizing substitution. So this is a little technique that sometimes is helpful, especially when we have a integral where there's part of our function is a root function. So you can kind of see the next example we're going to do. 1 over 4x minus 5 times the square root of x minus 1. We have this part of our function here involves a root function. And so the technique of rationalizing substitutions is it's another u substitution, can't get away from it, and we're going to let u equal that entire root function. And what's going to happen, what we're going to see when we go through this example, is this will rationalize our function so that partial fractions are going to be helpful. They're going to become applicable. So what are we going to do in this example? We're going to let u equal the square root of x minus 1. And that's going to make some significant changes here where we're actually going to do a partial fraction decomposition. If we're looking at this example, it's not a rational function because this square root term, that's not a polynomial. So partial fractions we can't immediately do it here. We also see the square root term. So let's kind of go down our checklist here. We can't immediately do partial fractions because it's not a rational function yet. We're going to do some work. We'll get it there. But as it's written right now, as this function is written, it's not a rational function. So partial fractions doesn't really apply. Now you see that square root term. You might also be thinking a trig substitution. But that's not going to work either because it's not of the correct form. So trig substitutions really only worked if we had things like square root x squared minus 1. That would be a trig substitution. We need our x to be squared because we know we're using trig identities there. We just have a regular old x here. And so partial fractions, as it's written, partial fractions doesn't work. And we see a square root, we might be thinking trig substitution, but that's not going to work because it's not of the correct form. So we're going to get started on this example with this rationalizing substitution. So we're going to try this. It's kind of a more clever U substitution that might not be the most obvious thing to try. So, this is something you might try after some of the other options haven't worked out. And what's going to happen is we're going to end up doing partial fractions. So let's get into it. All right, so we have this integral, 1 over 4x minus 5 times the square root of x minus 1. We know we can't immediately do partial fractions because it's not a rational function. It's not a trig substitution because it's not of the right form. It's not like a square root x squared minus 1. So we're going to try this rationalizing substitution. So we're going to let u equal the square root of x minus 1. And from here, we're going to solve this equation for x. Now notice, we'll get our differential. Normally when we do a substitution, we do our differential right away. We'll get there. But let's solve this for x first. So I would square both sides. So that would give me a u squared is equal to x minus 1. If I squared both sides, and then add 1 to both sides to get x by itself, and that would give me what? X is equal to u squared plus 1. All right. So this is going to help us convert over this kind of lone x term here. This, our original choice for u, is going to help us convert over that square root x minus 1 that we see. Now we still need to convert over our differential, and we could actually calculate our differential. We can calculate it from here, or we can actually calculate it from here. And that's what we're going to do here. We can calculate it from this equation. And so if we look at this equation, differentiating will give us dx, and it'll be the derivative of u squared plus 1 will be 2u times du. And so now we can actually just plug in directly because we know what dx is. It's 2u times du. So it has a slight, maybe we're doing things a slightly different order than we normally would with a regular u substitution, but that's really all we're doing here is just a u substitution. So we're letting u equal the square root term. We solved for x because there were some other x terms that we would have to deal with. And then actually solving for x probably allowed us to calculate the differential a little bit easier. We were able to see what dx is by just calculating the differential of u squared plus 1. It's 2u du. So now let's plug in all of our pieces. All right, so the 4x minus 5. Well, we know what x is. It's u squared plus 1. So let's fill that in. And then we have our minus 5. All right, so that's the 4x minus 5. We've replaced all of our pieces, our x pieces there. Now let's replace that square root term. So we know the square root of x minus 1 is going to become u. And then let's replace that dx, and we know what dx is going to become. It's going to become the 2u du. And this is always the fun part. We get some canceling. We can multiply this out and simplify. So we're going to end up with the integral of 2 over, let's distribute the 4. So we're going to get 4u squared plus 4 minus 5 du. And then the 4 and the minus 5 we can simplify a little bit further. And we end up with 4u squared minus 1 du. Now, as we look at this, what we've done is we've taken the problem, which originally was not a rational function, so we couldn't do partial fractions. And with this kind of clever u substitution, we're able to convert it into this problem now where this actually is a rational function. So partial fractions might be helpful. And that's what we're going to go through. We're going to go through the actual partial fraction decomposition of this rational function. And the denominator here is going to factor into two distinct linear terms. So it's not an irreducible quadratic, primarily because we have this minus 1. If that was a plus 1, it would be an irreducible quadratic. So it would be kind of the forms we've seen so far. But this is going to factor. So let's go through next. We'll work on doing this integral. We're going to go through the partial fraction decomposition. So let's actually start by factoring. So where are we so far? We have this 2 over 4u squared minus 1 du. And let's just keep track. We've done a u substitution where u is equal to the square root of x minus 1. Just to keep track here. All right. So now we want to factor. So when we have a rational function and we start our partial fractions, we want to factor the denominator. And this actually we'll kind of do this off to the side. So we're going to go through our partial fraction decomposition. And we're going to factor the denominator. So that's our first step. So here's our function, 2 over 4u squared minus 1. And it's going to factor. And it's going to factor into, well, we'll have 2 in the numerator still, but it's going to factor into 2u minus 1 times 2u plus 1. And you can check that out. If you get stuck on factoring here, you could always use quadratic formula. To help. And if you did that, you would see that u equals plus or minus 1/2 are the two solutions if we were to set this denominator equal to 0. And from that, you can see that we would have two factors here, 2u minus 1 and 2u plus 1. So, for instance, if you were getting stuck and you use the quadratic formula or you're able to solve this, being able to solve it really helps you figure out what the two factors are. So, if as an example, if we knew u was equal to 1/2, that's a solution. Well, multiply both sides by 2 to give us 2u equal to 1. Then subtract 1 from both sides. And right there on the left is one of our factors. So we would try using that as one of our factors. And then the other solution would give you the other factor, and then you just want to try multiplying them out to make sure that it actually does multiply out correctly. So you can use these solutions to help you figure out, if you're getting stuck factoring, you can use it to help you figure out the factors, kind of work backwards. So, solving it, we get u equals 1/2. Working backwards can kind of tell us one of the factors to try. So we would try 2u minus 1 as a factor. And it does actually work out in this case. All right, so we have this thing factored. Now we want to write out our decomposition. So it's going to be a over 2u minus 1 plus b over 2u plus 1. So we have different linear terms. So we know for each linear term that we have here, it gets its own fraction. So a over the first one plus b over the second one. And they're only repeated once. So we only have one fraction for each linear term. All right. So now we want to multiply both sides of this equation by the terms that are showing up in the denominator. So if we do that on the left, we're going to, the denominator is going to cancel. That's the whole point. So we're just going to end up with 2. And if we multiply it on the right, we'll actually see that. We'll work it out. So we're going to distribute. And when we take this term in the denominator, we're going to distribute it to the first fraction. And that's going to, the 2u minus 1s are going to cancel. So we're going to be left with 2 is equal to a times 2u plus 1. And then do the same thing. We're going to take this whole denominator piece that we're multiplying by, multiply it with the second fraction, and that's going to give us plus b. And here the 2u plus 1s are going to cancel. So we're going to have 2u minus 1 left over. And so now we want to solve this equation and figure out a and b. And we have some different ways to do that. We could compare coefficients. But we have different distinct linear terms here. So plugging in different u values might be helpful. And let's try out, well, what's our first linear term here? It's 2u plus 1. So that would correspond with u equal to negative 1/2. So we're going to be referring back to this equation to help us figure out a and b. So let's try what happens when u is equal to 1/2. We plug it in. We're going to have 2 on the left-hand side. We plug in the negative 1/2. That's going to cancel the term here with the a. So this whole thing will just become 0. Then we're going to have b. And what happens when we plug the negative 1/2 into here? We're going to end up with negative 1 minus 1. So we're going to end up with negative 2. And dividing both sides by negative 2 tells us our b value. It's actually equal to negative 1. Try another u value. So what is our other linear term? Where'd it go? We already did this one. So 2u plus 1, setting that equal to 0, gave us this u value to try. If we go to our other linear term, the 2u minus 1, that gives us u equal to 1/2. So if we plugged 1/2 into this, we would get 1 minus 1, which is just 0, and it's going to cancel out. So it'll cancel out this whole second piece. So let's see what happens when we plug that into the whole equation. We're still going to get 2 on the left. And then we're going to have our a. And then we'll have 2 times 1/2, which is just 1. So we end up with 1 plus 1, which is 2. And then plus b. And then 2 times 1/2 is positive 1, but then we're subtracting 1. So this is going to be just 0. So this whole second piece is just going to drop out. And we're going to end up with this equation. 2 is equal to a times 2, divide both sides by 2, and we get a is equal to 1. And so we can plug that into our partial fraction decomposition now. So we can actually rewrite this function that we're trying to integrate with the partial fraction decomposition. So what is it? Well, it was a over 2u minus 1, but let's plug in our a value. So 1 over 2u minus 1. And then our b value was negative 1. So I'm going to actually make that subtraction just to be a little easier. And so going through the partial fraction decomposition, that's what all of this work is. We've split up this rational function now into two separate fractions, 1 over 2u minus 1 and 1 over 2u plus 1. And now we can actually do the integral of those. So let's actually do that. So far we're still working on this integral. Takes a little bit of work. We're getting there. And we have 1 over 2u minus 1 minus 1 over 2u plus 1. So we still had to do a u substitution. That was way back now. We did u substitution where we let u equal the square root of x minus 1. That gave us a rational function that we could do partial fractions with. And here's our partial fraction decomposition. So now these are of the form we can just integrate. So what's the antiderivative of 1 over 2u minus 1? Well, it's going to be the natural log of the absolute value of 2u minus 1. So just take what's in the denominator and put it inside the absolute value there. Now we do have a constant term in front of our variable. So this is like one of our k-form. So we're going to take that constant 2, flip it, and put it in front. So we're going to have a 1 over 2 in front there. Then we do the same thing for our other integral. So we have minus. And here we're just integrating 1 over 2u plus 1. There's no extra powers here on the denominator. So it's going to involve the natural log of the absolute value of 2u plus 1. Now there is that extra constant there in front of our variable piece. So we're going to take that constant 2, flip it, put it in front. So there's our antiderivative now, all in terms of u. And to finish our work, we have to convert back. Our original function was in terms of x. Now we need to convert back. So we go through wherever we see a u, we're actually going to plug in what x is, or our x values. So we're going to end up with 1/2 times the natural log of 2 times the square root of x minus 1 minus 1 minus 1/2 times the natural log of the absolute value of 2 times the square root of x minus 1 plus 1. And then plus c. So we had to go back, and wherever we had a u here in our expression, we had to plug in square root x minus 1. And now we have our antiderivative. It's all in terms of x. We're done. So that's a nice kind of application of being able to do these partial fraction decompositions, is sometimes you can do these slightly, more clever u substitutions, gets you to a rational function, and then from there we know how to handle rational functions. Usually partial fractions is what we do. All right, so we're going to stop there for today. And next time we're going to be moving into more integration techniques. So we're going to end here with partial fractions. I think we've done enough examples. So we're going to see more integration techniques next time. So we'll see you then. Bye-bye.